Good afternoon, everyone. And welcome to this webinar. First, okay, good afternoon, everyone. And welcome to this first webinar organized by the European Membrane Society. I am Maria Grazia De Angelis, and I will chair this first webinar. So today's speaker is the president of the European Membrane Society, Professor Anthony Szymczyk. And I'm going to introduce him briefly, and I will leave to his seminar in a few minutes. So Anthony got his PhD in physical chemistry in 1999 from the University of Franche-Comté in France. He currently is a full professor at the University of Rennes in France, where he leads the chemistry and process engineering group. He was also awarded with the IUPAC Distinguished Award for Novel Materials and their Synthesis in 2013 for his work on ion transfer through nanoporous membranes. And his research lies at the interface between chemical engineering, materials chemistry, and condensed matter physics. His main research topics include the modeling and simulation of membrane separations for applications such as desalination, water purification, and physicochemical characterization of membrane materials, for instance, in association to problems like surface functionalization, fouling, and aging. And his research activity has been published in about 130 papers, 15 book chapters, and he has received something like 4,000 citations. Today, he's going to speak about the electrokinetic leakage phenomenon in zeta potential experiments, friend or foe. So in this webinar, the various errors that can result from not considering electrokinetic leakage during zeta potential experiments will be reported. And I will now leave the stage to Anthony, and I hope you enjoy the webinar, and we will take your questions at the end of the lecture.
Thank you, Maria Grazia. So, let me just sharing the screen. Okay. I hope everything is working now. Good afternoon, ladies and gentlemen, and welcome to this first webinar of the European Membrane Society. The current pandemic prevents us from meeting face-to-face and deprives us of these rich moments during which we can exchange ideas and experiences. So in order to keep in touch and allow us to further exchange and discuss, the European Membrane Society has therefore decided to organize a series of online webinars. The topic of this first webinar, as Maria Grazia said, will be the electrokinetic leakage phenomenon, which may arise during the electrokinetic measurements performed for the determination of membrane zeta potential. Here is the outline of this webinar. First of all, I will remind you with the basics of electrokinetic measurements. Then I will focus on the electrokinetic leakage phenomenon, its origin, the issues related to this parasitic signal, and the way to correct electrokinetic measurements for it. In the third part of this presentation, I will show you how to extract useful information from electrokinetic leakage and thus how to take advantage from this undesired phenomenon. And of course, I will conclude this webinar by a short conclusion summarizing the main take-home messages. So let's start with the various possible origins of the surface charge. The first possible cause is the presence of functional groups with either acid or basic properties, such as carboxylic acids or amines groups. This is the case for many polymer membranes, for instance. We can also find some amphoteric groups on membrane surfaces, such as metal hydroxyl groups present on the surface ceramic membranes. Structural defects can also be responsible for the surface charge, as it is the case, for instance, for clay materials. And last but not least, the specific adsorption of charged species from the solution onto the membrane surface can also lead to an effective charge density. The charged species at the membrane surface generates an electric field which propagates in the solution in contact with the membrane. Within the framework of the famous electrical double layer model, the zeta potential is defined as the value of the electrostatic potential at the hydrodynamic plane of shear between the stern layer and the diffuse part of the electrical double layer. The zeta potential is a very sensitive indicator of the electrostatic interaction between a membrane and the surrounding liquid phase. Since it is intrinsically accounting for specifically adsorbed species, its determination proves to be very useful when investigating problems of practical relevance. And zeta potential is now part of the toolbox when it comes to characterizing membrane materials. Zeta potential cannot be measured directly and can only be calculated by means of a model from the measurements of electrokinetic quantities, such as the streaming potential or the streaming current. There are Cousin techniques. In both cases, the excess of contrariance present in the diffuse part of the electrical double layer is set in motion by the application of an overpressure. Two electrodes are placed on either side of the material being studied. And if these electrodes are connected to a device with a very low internal resistance, such as an ampere meter, for instance, the streaming current can be measured. Conversely, if the electrodes are connected to a device with a very high input impedance, such as a voltmeter, then the contrariance can no longer be discharged in the low pressure compartment. The ends of the material becomes polarized, and an electrical potential difference, called the streaming potential, can be measured. In both cases, we are interested in the variation of the experimental signal, the streaming current or the streaming potential, according to the pressure difference applied through the system. And if all goes well, this variation is linear. And the slope of the electrokinetic curve, known as the streaming current coefficient or the streaming potential coefficient, allows the zeta potential to be calculated, for example, using the famous Szymczyk's model. From the experimental point of view, the easiest way to perform the electrokinetic characterization of membranes is to implement transversal or through-pore measurements. However, some issues limit the data interpretation with these transversal measurements. The first issue is related to the multi-layer structure of many commercial membranes, which makes the determination of the skin layer properties quite tricky. Another type of complication occurs with membranes having ion rejection capabilities. This is because the pressure difference applied during the measurements results in a transmembrane concentration difference to the membrane, which acts as a second driving force, thus causing a nonlinear variation of the signal with the pressure difference. In order to overcome this issue, tangential measurements, both tangential streaming potential and tangential streaming current measurements, based on the application of the pressure gradients along the membrane skin layer, have been developed and have become the most widely used measuring mode of both the streaming potential and streaming current. Usually it requires the two membrane samples facing each other and separated by a known distance, HCH in this schematic. The two membrane samples thus form a streaming channel through which the measurement is performed. The distance between the two samples is usually set from say, a few tenths to a few hundred micrometers. That is to say, this distance is much greater than the Debye length in the measuring solution, which is typically between a few nanometers and a few tenths of nanometers, depending on the ionic strength of the measuring solution. That allows the application of simple models, just like the famous Szymczyk's model, and thus it avoids heavy numerical processing for the calculation of the zeta potential. As I said before, this type of electrokinetic measurements has become very popular over the last, say, 2 or 3 decades, and it is now part of the toolbox for the characterization of membrane materials. Here are a few examples of applications, among many others. By analyzing the shape of the electrokinetic curves, in this example, that's the zeta potential or the function of the pH of the measuring solution, it is possible to determine whether or not different types of functional groups are present on the surface of membranes. Since the zeta potential includes both the effects of the surface charge and of the species adsorbed onto the surface, monitoring the temporal evolution of zeta potential can make it possible to study the adsorption kinetics of fouling species. Another application of great practical interest in membrane science is the detection of membrane aging under the action of various chemical agents. Depending on the type of the physical-chemical changes suffered by the membrane surface, this may result in a change in the amplitude of the electrokinetic curves or a shift of the isoelectric points, or also a change in the shape of the electrokinetic curves. However, complications have been pointed out when such tangential electrokinetic measurements are applied to membranes, for which a part of the streaming current is likely to pass through the membrane matrix, and not only on the external surface of the skin layer. From an electrical point of view, this amounts to considering an assembly of resistors in parallel. The total current measurable by the experimental device being distributed in the different branches, namely the streaming channel between the membrane surfaces of the two samples. This is the part of the signal we are interested in, but also within the matrix of each of the two samples. This parasitic contribution to the experimental signal, which I like to call electrokinetic leakage, has been largely overlooked in the literature, although, as we shall see now, it may lead to a relatively inaccurate determination of the zeta potential, or even to misleading conclusions about surface properties of membranes. Let's start by highlighting this electrokinetic leakage phenomenon. To do this, a series of streaming current measurements are carried out by varying the distance between the two membrane samples. For each distance, the streaming current coefficient is extracted, and it is plotted as a function of the distance between the membrane samples. As can be seen here for a PVDF membrane, synthesized by phase inversion, but without the addition of a pore-forming agent. This is the result shown by the blue symbols. The variation of the streaming current coefficient with the distance between the samples is linear, in agreement with the electrokinetic theory, and the extrapolation of the experimental data to a zero distance passes through the origin. This is of course obvious, since when the distance between the membrane samples is zero, then there is no streaming channel, and therefore no current can flow between the surfaces of the membrane samples. On the other hand, if the same type of experiment is carried out with a PVDF membrane synthesized under the same conditions, except for the fact that a pore-forming agent has been added to the polymer solution, we observe that the line no longer passes through the origin, which indicates that a current continues to flow through the measuring cell even if the two membranes are in contact. As there is no streaming channel when the distance between the samples is zero, this implies that this current is flowing through the bulk of the membranes. This is the electrokinetic leakage phenomenon. Its magnitude is expected to vary with the structural features of the membrane, the pore size, the membrane porosity, and the pore tortuosity. The electrokinetic leakage is also impacted by the membrane charge, since the streaming current results from the motion of the excess of counterions in the electrical double layer, and it also depends on the hydrophilicity or hydrophobicity of the membrane, which make it easier or harder the penetration of the measuring solution in the membrane matrix during the electrokinetic experiment. In fact, the magnitude of the electrokinetic leakage is also strongly dependent on the configuration of the measuring cell. In this figure, you can see the results obtained for the same membranes characterized using two different measuring cells, two cells having different designs. In the first cell, here at the bottom left, the thickness of the samples is totally exposed to the hydrodynamic flow during measurements, which favors the electrokinetic leakage phenomenon. On the other end, the design of the second cell, here on the right, is such that the lateral faces of the membrane are not in direct contact with the measuring solution as it flows between the two membrane surfaces. As a result, the electrokinetic leakage is much lower with the second cell than with the first one. Regardless of the cell geometry, the experimental signal can be corrected for the electrokinetic leakage phenomenon by subtracting the value of the electrokinetic leakage from the value of the streaming current coefficient actually measured in an experiment. After making this correction, then Szymczyk's conventional model can be used to determine an accurate value for the membrane zeta potential. Not making this correction can, as you well understand, can lead to significant errors in the determination of the zeta potential and can lead to, say, misleading conclusions if the electrokinetic leakage represents a substantial part of the experimental signal measured by the electrokinetic device. The next slide shows you the results of simulations illustrating the extent of errors that can be made if the electrokinetic leakage phenomenon is not considered in the interpretation of the electrokinetic data. In the top figure, I took the example of a membrane for which the zeta potential of the surface is exactly the same as the zeta potential in the porous sublayers. In the figure, the zeta potential of the surface and that of the bulk of the membrane are represented by the black line and the black symbols, respectively. In the absence of electrokinetic leakage, an electrokinetic analyzer, such as those commercially available, would therefore give us the black curve for the zeta potential of the membrane surface, which would be actually the correct answer. However, if the electrokinetic leakage occurs, the electrokinetic analyzer will provide incorrect zeta potentials, such as those shown by the blue, the green, or red curves, depending on the intensity of the electrokinetic leakage. Here, the only thing I have changed in the simulation is the effective depth of penetration of the leakage current in the membrane matrix. 20 microns for the results shown in blue, 40 microns or 60 microns. You can see that the error on the value of the zeta potential can be very large, the correct value being, I remind you, the black curve. The bottom figure shows that not taking into account the electrokinetic leakage phenomenon can also lead to errors in the determination of the isoelectric points of the membrane. This is the case if the isoelectric point of the surface layer is different from the isoelectric point of the membrane matrix, which can occur, for instance, with composite membranes. Now that we have seen the problems and issues associated with the electrokinetic leakage phenomenon, and also how to correct the experimental measurements for this parasitic phenomenon, we will now take a more positive approach and see how to take advantage of this phenomenon to go further in the information that can be extracted from electrokinetic measurements. For this first example, I've chosen to show you the results of streaming current experiments carried out with a nanofiltration PS membrane, polyether sulfone, that was exposed to sodium hypochlorite solutions for different times, ranging from 6 hours to 80 days. Measurements were taken at different separation distances between the samples in order to determine the intensity of the electrokinetic leakage. The table shows the contribution of the electrokinetic leakage to the experimentally measured signal, considering the signal measured at a distance of 100 micrometer as an arbitrary reference. In this case, the electrokinetic leakage represents around 11% of the total signal, of the signal that is available from experiments. The intensity of the leakage varies with aging, but the contribution of the electrokinetic leakage phenomenon to the experimental signal does not vary when the time of exposure to chlorine increases. On the contrary, when the same type of experiments are carried out with an ultrafiltration membrane, also in PES, an increase in the contribution of the electrokinetic leakage to the measured signal is observed as the time of exposure to chlorine increases. This suggests that the internal structure of the ultrafiltration membrane is impacted by aging, but not that of the nanofiltration membrane. It is also noted that the contribution of the electrokinetic leakage for the pristine membranes is greater for the ultrafiltration membrane than for the nanofiltration membrane, which is explained very simply by the greater porosity of the ultrafiltration membrane compared with the nanofiltration membrane. All right, the next slide shows the results obtained by carrying out the same type of experiment, but this time with a PVDF ultrafiltration membrane. The measurements were carried out with the same sample, but applying different pressures to circulate the measuring solution in the streaming channel. When the measurements were carried out by applying a pressure difference of 0.3 bar, no electrokinetic leakage was detected. This is most likely due to the relatively hydrophobic nature of PVDF, which prevents the entry of liquid into the membrane matrix. However, if the experiment is repeated, this time by applying a pressure difference of 1 bar within the system, then a slight electrokinetic leakage occurs and is detected. This suggests that the phenomenon of electrokinetic leakage could be used to determine the minimum liquid entry pressure in such membranes, which is an important feature, for instance, in membrane distillation related to the issues of membrane wetting. Let's go back to the schematic showing the separation of the experimental signal in the different branches that represent the streaming channel between the membrane surfaces to be analyzed and the membrane matrices. Szymczyk and Luxbara proposed this approximate equation for the total streaming current in a case of electrokinetic leakage. If we relate this equation to the electrokinetic experiments I presented earlier, we understand that the slope is actually related to the electrokinetic properties of the membrane surface, whereas the electrokinetic leakage depends on the electrokinetic properties of the membrane matrix, but also on the structural features of the membrane matrix. This can be exploited in the major issues of membrane fouling, for instance, but not only. This point is illustrated on the next slide, which shows the results obtained for a membrane having filtered an oil-in-water emulsion at two different working pressures. When filtration is carried out at low pressure, the results are shown here in blue in this figure, an increase in the slope is observed compared to the new membrane. But the electrokinetic leakage remains practically the same. This indicates that fouling only occurs on the surface of the membrane under these filtration conditions. However, when experiments is carried out at high working pressure, the slope further increases, indicating greater surface fouling, but the electrokinetic leakage disappears. This indicates that under these filtration conditions, internal fouling occurs in addition to surface fouling. The disappearance of the electrokinetic leakage is explained by the fact that when the oil penetrates inside the porous membrane matrix, then it cuts the conduction pathways in the membrane matrix, in the membrane porosity, thus preventing the circulation of the leakage current inside the membrane. As I said before, the electrokinetic leakage depends on the structural properties of the membrane matrix, but also on its electrokinetic properties. It is therefore possible to extract the value of the zeta potential of the membrane matrix from the value of the electrokinetic leakage. However, this requires the HF parameter to be determined beforehand. HF actually represents the effective penetration depth of the electrokinetic leakage. It depends on the thickness of the membrane, its porosity, and also on the pore tortuosity. In order to determine the slump parameter, additional electrical conductance measurements must be carried out. Indeed, in the case of tangential measurements, the HF parameter, so the effective penetration depth of the electrokinetic leakage, can be deduced by an extrapolation procedure, provided that the electrical conductance of the measuring cell, G cell, is measured for different separation distances between the membrane samples, exactly as we have seen with the streaming current coefficient in order to determine the intensity of the electrokinetic leakage. In this way, both the zeta potential of the membrane surface and that of the pores inside the membrane matrix can be determined. The next slide shows the results of this procedure, combining streaming current and electrical conductance measurements for different distances between samples of negatively charged polyether sulfone membranes functionalized by a species carrying a positively charged phosphonium group. It was thus possible to prove the presence of the positive phosphonium groups inside the membrane pores through the change in sign of the zeta potential of the membrane matrix before and after modification. Electrical conductance measurements performed at different separation distances between the membrane samples can also, say by by themselves provide interesting information. Here is an example of this. This is a study we recently carried out with Professor Alexei Volkov's team in Moscow. Volkov's group has shown that polymers with intrinsic microporosity, such as PMP for instance, are impermeable to water even when pressures of several tens of bars are applied through the membrane, even though this polymer absorbs a significant amount of water. They also showed that liquid transport through these membranes remained impossible with water ethanol mixtures until a threshold concentration of ethanol was reached in the mixture. This was interpreted by saying that adding a certain amount of ethanol allowed the clusters of liquids absorbed by the membrane to connect with each other and thus to generate percolation clusters, allowing liquid transportation through the membrane. Electrical conductance measurements performed in tangential mode confirmed this hypothesis. Indeed, it can be seen in this figure, in which the conductance is represented in the logarithmic scale, that the electrical conductance in the membrane matrix is almost zero as long as the threshold concentration of ethanol is not reached in the mixture. Above this threshold value, the electrical conductance of the membrane matrix becomes significant, indicating the connection of the liquid clusters in the membrane and the formation of the percolation clusters, allowing the transport of liquid under pressure. As a last example, I show you here in this slide the values of the specific electrical resistances of different commercial ion exchange membranes determined by this type of tangential measurements of electrical conductance. So here we have both anion exchange membranes and cation exchange membranes. And as you can see in this table, if you look at the results printed in red, the values obtained by the tangential measurements of electrical conductance are actually in very good agreement with manufacturer data. To conclude, this webinar focused on the electrokinetic leakage phenomenon that can interfere in electrokinetic measurements performed in tangential mode, which is nowadays the most commonly used measurement mode for membrane characterization. We have seen that this parasitic phenomenon can lead to incorrect interpretation of electrokinetic measurements, in particular to inaccurate values of the zeta potential and also errors in the estimation of the height electric point of membranes. We've seen how to take this electrokinetic leakage phenomenon into account and how to correct the experimental measurements in order to get an accurate zeta potential determination. Well, I've not addressed this point specifically, but since the membrane matrix is likely to contribute to both the streaming current and the electrical conductance, it is better to use the streaming current method rather than the streaming potential method, as the combination of the two effects can lead to a nonlinear variation in the streaming potential coefficient with the distance between the membrane samples, which can make the extrapolation procedure more challenging. Eventually, knowing that the electrokinetic leakage crosses part of the membrane matrix, we have seen how to extract the information it contains and how the electrokinetic leakage phenomenon is likely to extend the field of application of electrokinetic characterizations in membrane science. I would like to end this webinar by thanking my students and postdocs who have carried out most of the experiments I have shown you today. I'm convinced that there is still much to explore and to exploit about this electrokinetic leakage phenomenon. I hope that this webinar will make you want to move in that direction. Many thanks also to Dr. Maria Grazia De Angelis for the invitation to deliver this presentation, and to Dr. Marco Stoller for the technical organization of this webinar. Thank you, Marco.
Thank you. Thank you, Anthony, for this very interesting seminar. And I'm sure there are lots of questions. And if you have any questions, please write them in the YouTube chat. I will report them to Anthony. What is, Anthony, according to your opinion, the most interesting application of this technique beyond the traditional ones? Could it be useful, for instance, for gas separation membranes as well?
Well, the main interest for sure is that with a single kind of experiment, you can extract information of what happened on the surface, but also within the membrane. So, for instance, in my opinion, a great potential of the method is in fouling studies and aging studies.
Aging, yes.
Yeah, because depending on the on your application, of course, the probing the electrokinetic leakage can provide you with information both about the type of foulant that can foul your membrane in the pores, within the porous matrix, but it can also give you information about the potential structural degradation of the sublayers if we consider membrane aging, for instance. And I don't know so many techniques that can do that. We have very sensitive surface techniques, but they don't provide you with any information about what happens underneath the skin layer. And with this kind of technique, or this kind of protocols, I would say, you can extract both kinds of information: what happens on the surface and what happens underneath the surface.
By underneath, what order of magnitude? What is the size, the typical size that you can investigate?
Difficult to answer, because it really depends on the on both the structural properties of the membrane and also the hydrophilicity or hydrophobicity. I mean, you can, if you consider for instance, two membrane materials having the same, suppose they have the same pore size, the same porosity, the same pore tortuosity, so the same structure, the magnitude of the electrokinetic leakage won't be the same, depending if the material is hydrophobic or a bit more hydrophobic or a bit more hydrophilic. So the magnitude or the penetration depth of this parasitic phenomenon is very difficult to predict.
I see. We have some questions in the chat, so I will read them to you. One is from Helen. She's asking if it is possible to use this for ion exchange membranes, or if there is any problem related to a high membrane charge.
That's a very good point. Ion exchange membrane, I must say, are quite difficult, quite tricky to investigate with electrokinetic measurements. Nevertheless, as I showed in the last slide, we succeeded in applying this kind of method to characterize some commercial cation exchange membrane, but also anion exchange membranes. The main difficulty the main difficulty with this kind of highly charged membranes is the linearity of the experimental signal with the driving force. From my experience with most ion exchange membranes, the variation of the streaming potential, and the same for the streaming current, is no longer linear with the applied pressure difference. That makes the determination of the zeta potential quite complex, because most models that are used nowadays are based on this linear variation between the experimental signal and the driving force. So that's the main points. But we perform a series of experiments with these materials. If you perform both the streaming current and the streaming potential measurements in order to compute, for instance, the cell conductance, then these results are in agreement with each other. I mean, so the measurement is correct, but it means that some additional phenomena occurs with these very highly charged systems. So clearly it's more difficult. I wouldn't say impossible, but more difficult.
Okay, let's leave some chances that it can be done. Another question is related to thin films. They are asking you if you could also characterize thin films, such as thin polyamide layers, and what would be the depth resolution of the electrokinetic leakage in that case?
Yeah, not easy to answer still.
Yeah,
what I can say, based on the different kinds of experiments we already performed so far, is that the electrokinetic leakage phenomenon is less important if we consider reverse osmosis and nanofiltration membranes than ultrafiltration and microfiltration membranes. This is obviously related with the difference in terms of porosity. The more porous is the membrane, the more you can expect an important electrokinetic leakage. But I don't think that the contribution, this leakage current flowing through the membrane matrix, it does not pass through the skin layer of nanofiltration or reverse osmosis membranes. They are too dense, I think. It doesn't mean that the conduction cannot contribute. The conduction of the matrix cannot contribute, but I don't think that the streaming current, the leakage in terms of streaming current, can be important. At first, we thought that most of the parasitic signal could flow through the backing material of the membranes. But I should be careful with this point. But we perform a few measurements with membranes for which it was quite easy to peel off the backing material. And surprisingly, we obtain exactly the same result, the same electrokinetic leakage with or without the backing material. So my conclusion at this point would be that the leakage mainly occurs through the intermediate layer. If we consider this thin film composite membranes, I think that most of the leakage occurs through the polysulfone layer. So not through the backing material, and probably not through the very top surface layer, not the skin layer. Okay. But still, I think we have to multiply the number of experiments with as many materials as possible to be sure of that.
I'm sure that after this lecture, many more studies will be devoted to inspect the potentialities of this. So there is another question that was probably already answered by Mary Shabani. Asks for what about the case of ion exchange membranes?
Yeah, so as I said before, Not impossible, but much more tricky to do.
Okay, so Urmi Roy is asking us if there is a is asking you if there is a mathematical expression that can be derived to calculate the average membrane charge used in common models for nanofiltration. For instance, the DSPM1 using the zeta potential.
Yeah, of course, in this presentation, I focused essentially on very simple models, just like the Smolikovsky's model, because it is very convenient. But as I mentioned in the first part of the presentation, when you it's easier to perform through-pore measurements than tangential measurements, but a complication arises when the pore size is getting smaller, or of the same order of magnitude as the Debye length of the system. If this situation is to happen, then for sure, simple analytical models like Smolikovsky's models are no longer should not be applied anymore. And in that case, the only way is to perform, say, quite heavy numerical processing based on, typically you have to solve a system of equations involving Navier-Stokes equation and the Poisson-Boltzmann equation, for instance.
Okay.
But there are results in several papers already published in the literature. But that makes this kind of the analysis of the experimental data therefore becomes much more heavy to handle. Yeah, but it's possible. Yeah,
it is possible in principle.
Yeah.
Okay, I have another question from Hélène. She wonders whether you can identify the presence of more than one functional group in nanofiltration membranes.
Depends on what kind of functional groups. If these groups have different electrokinetic signatures, then you can. If they belong to the same, say, chemical family, that will be much more tricky. I mean, it's easy to differentiate, for instance, just consider the example of phenol groups and carboxylic acids, for instance, because they want their electrokinetic signature does not appear in the same region in the electrokinetic curve. But if the question is, can we separate the contribution? Can we distinguish between two different kinds of carboxylic acids? That would be much more difficult.
Okay, so I have
that's why most often we don't perform only electrokinetic measurements, but we combine electrokinetic measurements with spectroscopic techniques. Yeah, infrared spectroscopy or XPS or this kind of methods to have the information on the chemical signature, yeah, in addition to the electrokinetic signature of the system.
I see. Okay, I have a couple of, well, I have actually a question from Mingliang Chen, and saying that it is really hard to measure the zeta potential of ceramic microfiltration, ultrafiltration membranes, I guess, due to the liquid leakage problem, as the flow check is bad. And the question is, do you have any experience in this? And is it possible to measure tubular membranes directly instead of the flat sample?
Yeah, so we have experience also, and it's true that characterizing flat sheet ceramic membranes, especially microfiltration or ultrafiltration ceramic membranes with these commercial, say, standard commercial devices, using tangential mode is very difficult. And my point is that it is very difficult because in this case, the electrokinetic leakage phenomenon is not a small part of the signal. It can represent the majority of the experimental signal, because typically ceramic membranes are very thick, say 1 or 2 millimeters in thickness. And if the design of the cell is such that the thickness of the samples is exposed to the hydrodynamic flow, then probably a significant, a very, very important part, substantial part of the signal will flow through the membrane porosity. That makes the interpretation, if the interpretation is made with a simple approach, probably totally wrong. Yeah, we had this quite strange experience in the past with some ceramic samples for which, when we changed the distance between the separation distance between the two membrane samples, then it was not possible to see a variation of the electrical current measured by the system, which is really, really surprising, because if you decrease the distance between the membrane samples, then the resistance of the streaming channel is changing, then the current should change. But the reason was that actually the part of the current flowing through the channel was very small, and most of the signal was actually flowing through the membrane matrix, and this contribution is not impacted by the separation distance. So yeah, ceramic membrane can be very difficult. The solution, I would say, if you want to perform these tangential measurements with flat sheet ceramic membranes, then it's better to work on the design of the measuring cell, and to develop a cell with which the thickness of the membrane is not exposed or not totally exposed to the hydrodynamic flow. This is possible, with if you take the example, for instance, of floor tiling, then you need to drill a kind of groove in the holder, put your membrane, you put a seal all around the membrane, and that should work. Maybe not. I'm not saying that you can totally remove the electrokinetic leakage phenomenon, but proceeding this way, it should be possible to decrease it significantly.
Okay, now you are disclosing all your secrets.
There is nothing secret at all. And I think the last part of the question was about tubular membranes.
Yes. To characterize tubular membranes directly.
Yeah. Then still the problem, if you want to do tangential measurements, is that as you saw in the schematics I've just shown, you must be able to generate a pressure difference along the surface. So it's possible with flat sheet membranes because the distance between the two membrane surfaces can be lowered down to 100 micrometers or a few tenths of micrometers. But if we are talking about tubular membranes with internal diameter of, I don't know, close to 10 millimeters, then if you want to generate a pressure difference along the channel, then you will need to use a very, very long membrane. So that's the problem. In this situation, it's better to use transmembrane transversal measurements. But if we are talking about fibers, hollow fibers, then it's possible to perform a tangential measurement with hollow fibers.
Yeah.
But extremely difficult to extract the electrokinetic leakage because the geometry of the system is fixed. With flat sheet membranes, because you are using two different samples, you can use we call it adjustable gap cell, in order to adjust the distance between the two surfaces. But if you perform the measurement through the internal diameter of the hollow fiber, then the geometry is fixed. So yeah, You can do the measurements, but it will be much more difficult to extract the electrokinetic leakage from the experimental signal.
Okay, I have another question from Carolina. She wants to know more about biomimetic membranes. If you have any idea whether there is an influence of biological elements on your type of measurement.
If the biological element has an electrokinetic response, then you can, in principle, detect it. The problem with biomimetic membranes is that the loading of the biomimetic material is extremely low in the membrane. In the membrane, so that's a common problem with characterization techniques. Yeah.
Mm-hmm.
Yeah.
Okay. Let's see if there is any other question. Appearing, last minute question. There is a certain delay between your response and the YouTube streaming, so. Okay, there's a new question by Gosh. How reproducible is the electrokinetic leakage current?
It's no difference in terms of reproducibility if you talk about the electrokinetic leakage or the standard measurement.
Mm-hmm.
The same. Depends on a lot of factors. But well, I'm not sure if I catch exactly the meaning of the question. It's true that still from our experience, then as I said before, the amplitude, the magnitude of the electrokinetic leakage depends for sure on the structural features of the samples, the charge of the samples, the hydrophilicity, hydrophobicity of the samples, also on the design of the measuring cell. But with some samples, it's true that it also depends on you. How will you fix your membrane samples onto the sample holder in the measuring cell? Depending on the material, if we consider, as we mentioned before, the very thick ceramic membranes, it's not a problem. But when you are working with thin films, then there is a kind of know-how, I would say, to fix your samples. And if you cannot manage this very precisely, for sure it can generate much less reproducibility. But if you have this experience, I would say that the reproducibility in terms of electrokinetic leakage is the same as for the standard electrokinetic signal. Yeah.
Okay. So if they want more details, they can visit your lab. Maybe not.
Sure.
Maybe not at this time.
Yes, we have to delay a little bit.
Not the best time.
Hopefully in 2021.
Yeah, exactly. So they can study all the tricks of the trade. Okay, I think that was the last question that I can see on our chat. And of course, you can contact Anthony via email if you have further questions. And I'm very happy to.
Yeah, sure. Don't hesitate.
I'm we managed to organize these webinars, and we are planning to organize more webinars in the future, especially if this situation continues. And thank you, Anthony. Do you have anything else to say? Any announcement?
Just maybe, yeah, just to remind everyone about.
Yeah, right. Our initiatives.
Yeah. So just take this opportunity to remind you, if necessary, of the HICOM 2020 conference to be held in December from 7th to 11th. That's so, as you know, this event is organized under the umbrella of the European Membrane Society only once every 9 years. Yeah. And of course, this year it will not take place in person this time, as we would have liked, but the conference chairs, Professor John Chu, Professor Kangley, Professor Andrew Livingstone, and Professor Davide Mattia, have made everything possible to enable us to attend this unique event online. So, yeah, on behalf of the European Membrane Society, I would like to thank them very much for their commitment to the membrane community. Yeah.
Good. So thank you, Anthony.
Thank you very much. Grazie.
Thanks to Marco Stoller for it.
Thanks to Marco, yeah, for all the technical organization.
Yes, and thanks to the audience, and
Yeah.
see you during the next seminar, and hopefully also during the ICOM meeting. Bye, everyone.
Thank you. Bye-bye.